The Hoover Dam is a triumph of civil engineering. A spectacular edifice of sculpted concrete, rising majestically in an imposing canyon, taming a wild river once thought to be tameless. A colossal statement, man conquering nature. But if there was no Hoover Dam, and one must be built, how would engineers build it today? What would they do differently? And what would stay the same?
Obviously, those all
How could we reinvent the Hoover Dam? The Hoover Dam is an American icon. The United States Bureau of Reclamation built it in the 1930s, and it's been the model of modern dam engineering ever since. It has three main purposes: to harness the wild Colorado River and control flooding, to store water to irrigate vast desert farmlands and quench the thirst of growing cities such as Los Angeles and Las Vegas, and to provide clean, consistent power to the American Southwest, enabling a population boom unmatched in history. To do so required a monumental engineering achievement.
When you consider that the Colorado River had been running through Black Canyon for millions and millions of years, actually cutting the canyon in many places, to have been able to move the river, first of all, and then to put this enormous chunk of concrete right in the middle of it was a feat of engineering wonder that had never been done before.
When completed in 1935, the Hoover Dam was called the eighth wonder of the world. Rising 221 meters, it contains 6 million tons of concrete, enough to pave a road from New York to Los Angeles. A gigantic concrete pyramid wedged in a desolate canyon, straddling the Nevada-Arizona border, 56 kilometers from Las Vegas. The reservoir created by the Hoover Dam, Lake Mead, covers 620 square kilometers and has a storage capacity of over 35 trillion liters, enough to cover the entire state of New York in 30 centimeters of water. Hoover's hydroelectric power plant has 17 generators, capable of producing 2 million kilowatts of electricity, enough for 1.7 million homes.
I think it's one of the examples of an engineering project where a group of people came together and achieved a very advanced goal as far as the quality of thinking through engineering from beginning to end.
But what if the Hoover Dam were built today? What changes would engineers make? And what would they do the same? Would the dam have the same design? Could the reservoir store more water? Could the power plant make more electricity? And what about the environment, above and below the dam?
They really didn't have a sense in the 1930s of ecology and what kind of damage might be done that they couldn't even imagine. They've only begun to realize that in later years.
There's this ridge here and this ridge here that are huge natural abutments.
We asked a team of engineers, hydrologists, biologists, and dam construction experts to consider these questions and tell us how they would reinvent the Hoover Dam. To begin this complex reinvention, one must first imagine the location before the Hoover Dam was built. Step 1. Choosing a location. The original survey work was conducted by the Bureau of Reclamation, using the best tools of the day: plane table surveyors for topographical mapping, transits for measuring terrain, and precarious drilling barges barely anchored onto the unruly river, used to drill core samples of bedrock. Today's survey tools would include GPS imaging of the landscape, laser sighting transits, and computer-aided design software to draft blueprints.
Our biggest advantage, you'd have to conclude the computer, just the computer system in general.
We also have the ability to do aerial survey in a lot more precise manner.
This includes aerial photogrammetry, a sophisticated means of mapping three-dimensional terrain using digital aerial photographs. These modern surveying tools give geologists and engineers a much better picture of the topography and geology of proposed sites. In the 1930s, three considerations were important to choosing the original location. First, the type of geology of the canyon walls and the depth to the bedrock on the river floor. The rock needs to be strong enough to withstand tremendous loads of water pressure. Second, how much water could be stored in the reservoir. The more water, the more human benefit. And third, proximity to population centres and major lines of transportation to bring in manpower, equipment and resources to build the dam.
The process for finding a location for the dam in today's world begins with scanning a lot of topographical maps like this one here. What you're looking for is to let nature, let topography, the existing terrain work in your favor.
After years of study, government surveyors and engineers concluded that a dam of suitable size and storage capacity could be built at one of two locations on the lower Colorado River, in Boulder Canyon or 32 kilometers downriver in Black Canyon.
The Boulder Canyon spot was the one that the government favored for a variety of reasons. But in March 1928, when the St. Francis Dam burst north of Los Angeles and killed hundreds of people, caused millions of dollars worth of damage, the government decided to go back and take a second look at what they were going to do on the Colorado River.
The 1928 St. Francis Dam rupture was a crippling blow to the engineers who built it, and a wake-up call to those building Hoover Dam. Wanting to avoid a similar disaster, government engineers re-inspected both sites more thoroughly and found flaws in the geology of Boulder Canyon. The canyon walls and river bedrock had more fractures and faults, making it less stable. They also determined that a dam in Black Canyon would store more water than one in Boulder Canyon. Finally, Boulder was further away from the nearest railroad lines and population center, Las Vegas. So the government decided the dam would go in Black Canyon.
Original designers of Hoover Dam found an ideal location. After I looked at the topography in great detail, I came to the conclusion that there's no doubt they made the best choice by far.
Our reinvention of the Hoover Dam will be built in the same location. Black Canyon is desolate and severe. A deep, hot crack in the Mojave Desert, miles from the nearest vestige of civilization. No place for human comfort or survival. In the summer, temperatures routinely rise above 49 degrees Celsius on the canyon floor. In the winter, they fall below freezing. It's a hostile environment and the perfect place for a dam. But what kind of dam? In 1930, just 2 years after the catastrophic St. Francis Dam collapse, the US Bureau of Reclamation chose an ultra-conservative gravity arch design, which combines two basic engineering concepts.
First of all, gravity, that implies that it's very bottom-heavy, and in fact, Hoover is. It's 660 feet thick, front to back at the bottom. So it resembles a pyramid, so very bottom-heavy, very stable with gravity. And then the upper part that's most visible and prominent is that nice graceful arch shape across the front. And that is a very efficient structure for routing the loads of the water pressure behind the dam into the canyon walls on both sides.
Our reinvention team also envisions a gravity arch dam, but with significantly different dimensions.
I certainly wouldn't start out with an ultra-conservative design. We don't have to have quite as much arch, and we don't have to have quite as much width at the base in order to get the strength needed to hold back the waters.
What the team proposes is a narrower dam and much taller, as much as 43 meters taller, capable of storing more water in the reservoir and creating more water pressure for power generation. But that's just the beginning. The original builders of the Hoover Dam faced many challenges. The first, how to get the manpower and equipment to such a remote location as Black Canyon. To begin with, there were no roads to the construction site. Those had to be blasted out of the steep canyon walls. 50 kilometers of railroad track also had to be laid to connect the construction site to the Union Pacific's main line outside Las Vegas. All built in an environment not suited to human life.
Workers came down here to find, first of all, the working conditions almost inhumane. The heat from the canyon, the wind, the lack of cold water, the lack of facilities. It was really a miserable time for workers.
Housing was also a problem.
Having a place for the labor to live in the desert wasn't an easy challenge here. Living in a tent in the desert is what you were up against.
When construction began in late March 1931, there were no provisions for a workforce that would eventually reach 5,000 laborers a day. The original builders, the Six Companies Corporation, planned to construct a company town near the project. But that community, Boulder City, took almost a year to complete. Until then, workers lived in tents and ramshackle bunkhouses along the river with no ventilation or running water. In any reinvention of the Hoover Dam, the harsh elements would be the same, but worker conditions would be much improved by modern technology. Prefabricated living accommodations would be provided for all workers before the first day of construction. On-site structures with air conditioning would provide necessary relief. Advanced machinery and construction equipment would eliminate much of the tedious manual labor and decrease the size of the workforce by as much as 50%. And there will be one simple but significant piece of equipment for every worker: a hard hat.
Today, there's no question, you don't show up on a job like that without a hard hat and steel-toed boots. But that's just the beginning. I don't think they used any safety nets in the construction of the Hoover Dam. There's no question that we'd use them today.
Safety measures were minimal at best. Officially, a total of 112 men were killed during the 5 years of construction at the Hoover Dam. In any 21st century reinvention, our experts predict a different number.
You would expect no casualties. At least you would be striving for no casualties.
You may think cost, you may think schedule, but safety has always been the #1 factor in all construction projects.
The first major task of any dam construction project is the diversion of the river that is going to be dammed. The work site must be completely dry before work can begin on the foundation. The time-tested method of river diversion is the construction of diversion tunnels. In the 1930s, the builders of the Hoover Dam spent nearly 2 years drilling 4 enormous diversion tunnels through the rock canyon walls. 2 tunnels on each side of the river. Each tunnel has a 17-meter diameter and is about 1,200 meters long. Altogether, the 4 tunnels are capable of moving enough water to fill 2 Olympic-sized swimming pools every second. The method of tunneling in the 1930s was also time-tested. Drill, blast, and muck.
And it means just what it says. You drill the holes, you put dynamite in each hole, you blast the dynamite, and then you muck out the rock.
Crews used an improvised truck called a jumbo. which allowed as many as a dozen workers to drill the face of the tunnel at the same time. The excavation was done in sections. First, the top or heading of the tunnel was blasted and mucked. Then the middle, or bench. And finally, the bottom, or invert section. As each section is drilled and blasted, it is then reinforced with steel. By using the jumbo, the builders of Hoover increased tunneling speed and excavated as much as 14 meters a day. But it came at great peril, because there was no ventilation in the tunnels.
They were running trucks, internal combustion engines in this enclosed space. So many workers were gassed with carbon monoxide. Some of them died because their pulmonary system was weakened from the gases.
Today, our reinvention team proposes a radical redesign of the diversion tunnel system at Hoover. Instead of 4 river diversion tunnels, they would build just 2, one on each side of the canyon. They would be the same length as the originals, about 1,200 meters. But they would be much larger, 21 meters in diameter. The team would also use a state-of-the-art method of tunneling.
The method we use is going to be called the New Austrian Tunneling Method, or in short, it's called NATM, N-A-T-M.
Here on the coast of California, near Pacifica, the California Department of Transportation, Caltrans, is using NATM to build 2 new bypass tunnels along a treacherous stretch of Highway 1, known as Devil's Slide.
Well, this project's been in the works for about 50 years to bypass this geologically unstable portion of the coast highway here.
The engineers digging these tunnels are very familiar with the tunneling done at Hoover.
This here is very similar. It's also a top-heading bench excavation, and in some areas also invert, but only the technology has changed. And of course, it's a much safer operation than it was at the Hoover Dam.
We're using some state-of-the-art equipment. We have been able to bring the latest technology that is being used in Europe, their latest methods and their latest technologies here in this project.
Using a fully automated laser scanning system, every 2.5 centimeters of the face of the tunnel is measured and mapped before excavation. This ensures that the tunneling is going in the right direction. Depending on the hardness of the rock, engineers then choose a boring method.
There are 2 methods which the contractor can choose. One is drill and shoot, and one is using the rotator. And in harder rocks, he has to use the drill and shoot method, and when the rock gets softer, then he's using the rotators.
The roadheader is an enormous excavating machine that grinds the face of the tunnel. In 4 hours, it can chew out 2 meters of rock. After each step forward, the tunnel walls are braced with lattice girders and then reinforced with shotcrete, a type of concrete that seals the tunnel walls. The entire process is geared for worker safety, precision, and increased productivity.
A lot of the equipment can be controlled without being in the area where the actual unsafe conditions may exist. So as you move forward, you do a few meters or a meter of excavation. You can do that all under the cover with robotic arms.
Using the NATM system, Caltrans excavates about 4 meters of rock, dirt, and gravel a day. Not quite as fast as the original excavation at Hoover, but with much greater efficiency and far less danger. In the redesign of the Hoover Dam, the 2 new and larger diversion tunnels would both be excavated using the NATM system. It would take about a year to complete the tunnels, half the time needed for the 4 tunnels built in the 1930s. And because of increased safety standards and sophisticated tunnel ventilation systems, the expected casualty rate would be 0. Once the tunnels are completed, engineers can safely divert the Colorado River and begin to prepare the canyon floor for construction of the new dam. In the 1930s, contractors began this process by completely drying the riverbed, then excavating loose dirt and sediment down to the bedrock. They also cleared the canyon walls of all loose rock to make smooth abutments for the concrete dam. This work was called high scaling. Workers swung from ropes hanging high over the canyon and chiseled the rock from the walls with jackhammers and sledges. These daredevils were the highest paid workers on site, earning $5.60 per day. And they were the most sensational to watch. In today's reinvention, high scaling would also be done in a similar fashion, but with much better rock climbing equipment, nets, and safety procedures. When the United States Bureau of Reclamation designed the Hoover Dam in the 1920s and 30s, they adopted an ultra-conservative gravity arch approach to eliminate any possibility of a catastrophic failure.
They built the dam with both an arch shape to hold back the pressure of the water, and then just for good measure, they built it as a gravity arch. So it's a combined thick dam and arch dam.
The result is a gigantic immovable concrete pyramid in the middle of Black Canyon, larger than the Great Pyramid of Giza. The dam contains 3.4 million cubic meters of concrete, weighing 6.6 million tons, enough to build a meter-wide pavement around the Earth at the equator. Using this much concrete, the builders expected the dam to last for hundreds, if not thousands of years.
Hoover Dam was far and away bigger than anything that had been built and attempted. And so those designers wanted to make sure that it would last almost forever and be stable and serve its purpose, but would never have an accident or be the cause of a flood as well.
The first bucket of concrete was poured on June the 1st, 1933, and the pouring continued non-stop on a 24/7 schedule. Because the temperature of concrete changes as it is poured, engineers calculated that it could take more than 100 years for the dam to cure if built in a single continuous pour. It would also be prone to damaging cracks. So contractors poured the concrete into a series of interlocking blocks. Wooden forms for each block measured up to 18 meters square and were about 1.5 meters deep. Even in these small forms, cooling the concrete was still a challenge due to the intense summer heat in the canyon. Engineers calculated that the internal temperature of the concrete rose 22 degrees Celsius from 49 to 71 degrees. To solve this problem, the original builders installed a grid of pipes in each block and ran cold water through the pipes after the concrete was poured. In all, they used nearly 1,000 kilometers of piping. In March 1935, after 2 years of pouring concrete, the imposing, magnificent edifice of the Hoover Dam was finally complete. Our reinvention team sees a different edifice in Black Canyon. They envision a dam rising 43 meters higher than the original, reaching 264 meters above the canyon floor. At this height, a reinvented Hoover Dam will be among the 10 tallest dams in the world. Our engineers have also designed it to have a longer length, 531 meters across the canyon, with a base width of 142 meters, but a wider crest width at 21 meters. It's a sleeker, taller design than the original, capable of storing more water in the reservoir and generating more electricity. Because of the increased overall size of the dam, this reinvention would require slightly more concrete than the original Hoover Dam.
You're looking at overall in the neighborhood of about 4,500,000 cubic yards of concrete, which is a rather large amount of concrete.
The composition of the concrete, cement, sand and rock, would also be different.
In the 1930s, Type 4 cement, which is a low-heat, relatively coarse-ground cement, was a typical cement that was used on large-scale projects such as dams. Today, that type of cement is not available in the western United States. What has been used in recent years is a low-heat version of Type 2 cement, which is slightly different in chemical properties.
The issue with Type 2 cement is cooling.
I estimate that with the dam that we're talking about here, we will have an average temperature gain of approximately 50 degrees with the post-cooling.
And we're going to deal with that by refrigeration.
Cold water, ice, and nitrogen.
Specifically, liquid nitrogen, which is injected directly into the concrete right before pouring.
It's typically only used in areas where you have really high ambient temperatures or where you need to have really low concrete temperatures.
Using modern equipment, our team estimates that it would take about 2 years to pour all the concrete for the larger redesigned dam, the same as the original. By raising the height of the dam by 43 meters, our reinvention team estimates it would nearly double the storage capacity of Lake Mead, enough to cover the state of New York in 60 centimeters of water.
One of the major reasons for wanting that type of storage or that amount of storage is that it gives the dam operator a lot more flexibility to decide when to release water.
This increased height and storage capacity would have a direct impact on the hydrology of the dam and the power plant, especially on water pressure and power generation.
We're taking advantage of the additional pressure or hydrostatic pressure from the water body. In this particular case, we're increasing the height of the water body by approximately 140 feet. In doing so, we are essentially increasing the power generation capacity up to about 20%.
The key structures for supplying water to the power plant are the intake towers. As originally designed, the Hoover Dam has 4 intake towers, 2 on the Nevada side and 2 on the Arizona side. Each tower is 120 meters tall, and each feeds water to the power plant through a network of pipes called penstocks. These intake towers were built to draw water from 2 levels of the reservoir, from the bottom and from the middle. When drawn from the bottom, the water pressure is much greater, which increases the amount of electricity the power plant can generate. The first purpose of the Hoover Dam is flood control. The second is water storage. The third, which actually pays for the operation of the dam, is power generation.
We live and breathe energy conversion at Hoover.
Put simply, Hoover uses the water from Lake Mead to spin huge turbine water wheels that crank the massive generator units to make electricity.
A hydropower plant like Hoover Dam makes use of the gravity and the weight of the water in the reservoir. So Lake Mead is roughly 500 feet deep. Well, that kind of water pressure at the bottom of 500 feet of water, that's a lot of available energy. And so if you route that to a water wheel, which will cause a shaft to spin, connect that to a generator, and you can harness that energy and convert it into electricity.
The U-shaped Hoover power plant is located on the sides of the canyon walls, at the bottom of the dam. Between 1936 and 1961, 17 generator units were installed in the power plant, 9 on the Arizona side of the dam, 8 on the Nevada side.
Hoover Dam was originally built with some of the biggest equipment that was available and the best technology that was available.
We got lots of big machines, really literally millions of pounds of spinning machinery that makes millions of watts of power, clean, renewable hydropower.
The original turbines were made of cast steel. They were capable of generating 80 megawatts each. In the 1980s, the Bureau of Reclamation retrofitted the power plant with new turbines capable of generating even more power.
They were retrofitted to be capable of 130 megawatts, a really substantial increase.
These second-generation turbines are designed for higher stress loads and improved water flow.
Each one is about 35 tons of stainless steel, and this 35 tons of stainless steel might be 16 or 18 feet in diameter and about 6 feet tall. We run 3,200 cubic feet per second of water.
The force of the water spins the giant turbine wheel at 180 revolutions per minute, or more than 160 kilometers per hour.
The water flows horizontally into the turbine from all sides, down through the turbine to produce the horsepower, and then exits out in the river.
At full bore, the Hoover Dam's power plant has the capacity to deliver 2,080 megawatts of electricity at any given moment. Enough power for 1.7 million households.
We try to get as much electricity out of the generator as we can get.
But hydroelectric engineers are always looking to increase capacity and performance.
We're in a continual state of change from an equipment standpoint, trying to get the most energy and the most value out of the equipment at Hoover Dam. It's really, in our mind, it's a national priority.
Today, the USBR is already in the process of reinventing its power plant at the Hoover Dam.
We continually look at technology. Technology is your ally in any energy conversion business. We look at turbines which can operate efficiently at many different lake elevations.
When the lake level fluctuates, it directly affects the amount of water pressure driving the turbines. The higher the lake, the higher the water pressure. Today, Lake Mead is about 30 meters below normal capacity, so the water pressure going through the penstocks to the turbines is decreased.
This screen has a ton of information. It's a snapshot of what's going on at Hoover right now, how the machines are operating, how much water is flowing. If you look at the column right here, the green numbers in this column show the millions of watts being produced by each Hoover unit. Hoover units are numbered with N for Nevada units and A for Arizona units. Unit N1 right now is making 100 million watts. We say 100 megawatts. N4 is making 92 megawatts. And the water to produce that power is shown down in the lower right-hand corner. It's 39,800 cubic feet per second. If we multiplied that out, that'd be roughly 300,000 gallons of water a second. That'd be 30 swimming pools a second. That's a lot of water.
The problem at Hoover is that power production is limited by the elevation of the lake, which dictates the water pressure driving the turbines.
My existing turbines don't necessarily operate as efficiently as they could at all these different lake elevations. The modern design turbines operate efficiently with what's called a balanced pressure blade design at many different lake elevations. That's one of the things that we have on the drawing boards.
Making more electricity is all about getting a water wheel to spin faster with the same amount of water pressure. And the next generation hydroelectric turbines do this. These are already in use at the Three Gorges Dam in China. They borrow technology from the aerospace industry. The individual blades are curved like jet turbines for improved water flow efficiency, making them capable of handling greater loads. But more importantly, they can spin faster with the same loads, which will increase power efficiency at Hoover. Our reinvention team has its own ideas about the power plant and control systems. Firstly, they would seek to increase water pressure to the turbines by increasing the overall height of the dam and the intake towers.
One of the major benefits of a higher dam is that when the water is at a higher elevation, you've got more pressure, and pressure is part of what runs the turbines and creates energy.
They will be spinning faster. Power generation increase will likely be about 20%. So we're looking at probably about 150 megawatt per unit at this time.
By installing these next-generation turbines, Hoover will increase its power efficiency once again. But as the engineers who operate the Hoover Dam look to the future, they face other critical challenges that the original builders of the Hoover Dam could never have imagined. On February the 9th, 1935, the builders of the Hoover Dam closed the river diversion tunnels and began to impound water in the new reservoir, giving birth to Lake Mead. 6 years later, in August 1941, the water level finally reached the height of the spillways, just below the crest of the dam.
They wanted to test the spillways and see if they were going to work. They were hoping they would work, and they did.
For the designers and builders of the Hoover Dam, it was a moment of triumph and relief. The dam was functioning exactly as planned. But they didn't give a thought to the ecosystems that were being destroyed in the process.
I would imagine that, without saying that they didn't care about the environment, as a decision-making criteria, it probably wasn't taken into consideration. I would imagine that coming out of the Depression era, trying to put people back to work was a primary concern of the federal government.
The river was very rich with flora and fauna, and the rising of Lake Mead destroyed all that.
Today, there are a variety of environmental issues facing the Hoover Dam that must be addressed now and in the future.
Our environmental concerns include invasive species. And in fact, over the past year, Lake Mead and much of the Colorado River system downstream is now affected by something called the quagga mussels, a variety of zebra mussels, very small clam-like animals, and they're very prolific, so they grow and breed quite rapidly. They have the characteristic of being able to clog up machinery in power plant piping. That is an environmental situation we're now managing at Hoover Dam.
The quagga mussel is not just a problem at Hoover. It's a ubiquitous problem for dam operators around the world.
This is an immediate issue that needs to be put into the design to make sure the facility can handle any potential intrusion of quagga mussel, to control it, to prevent it from entering our system, and if it can enter into our system, how we can deal with it to eliminate that.
We're looking at a couple of very environmentally friendly filtration techniques. We'd like to do some sort of filtering as opposed to chemical treatment. So that's our emphasis at the moment.
Eradicating the quagga mussel is just one concern for our reinvention team. They're also looking carefully at the ecosystems above and below the dam.
One of the major issues with the dam will be that we are creating a unique habitat. We're creating a lake where before there was only flowing water. And the other thing we're doing to the river below the dam becomes highly modified. Instead of rising suddenly, it becomes very stable.
Because the primary purpose of any dam is flood control, the natural cycle of flooding is eliminated from the downriver reaches, and the river ecology is forever altered. The river loses nutrients and the regular flow of sediment. Sediment is vital to any natural river environment. But when sediment cannot pass through a dam, it piles up in the reservoir, sometimes rising to damaging levels.
Now, when Hoover Dam was constructed, a delta of sediment was formed at Lake Mead, 42 miles long. That sediment, that sand and gravel, belongs to a river, belongs to the downstream reaches. It does not belong in a reservoir.
Sediment removal is also extremely expensive. At Lake Powell, where the sediment buildup has exceeded the design levels behind the Glen Canyon Dam, the estimate for removal is $83 billion.
To remove $83 billion of sediment from Lake Powell is beyond imagination, beyond accepted economics. If we have to redesign the Hoover Dam, or any dam for that matter, we should take into consideration of passing the sediment around the reservoir, bypass it.
The Japanese have pioneered an innovative solution to this sediment problem. Here at the Asahi Dam, they've constructed a tunnel around the reservoir to carry nutrient and sediment-rich river water downstream of the dam. It's an idea that the Hoover Dam reinvention team has embraced.
My concept would be to have a tunnel through the rock, around the reservoir, downstream of the concrete dam, and let the sediment be discharged downstream of the dam.
The reinvention team proposes an 85-kilometer-long concrete-lined tunnel or pipeline, 6.7 meters in diameter, reaching from the mouth of Lake Mead to a point downstream of the Hoover Dam. To build this long tunnel, our team would not use the new Austrian tunneling method they suggest for the river diversion tunnels, but instead would use another method, a tunnel boring machine, known as a TBM. This massive beast bores long tunnels like a mole.
You can take advantage of the cost advantage or the economics of a TBM because you build a TBM once and you can drive a long distance. And the diameter of tunnel is feasible for a tunnel boring machine for the sediment tunnel.
Once built, this innovative sediment tunnel would solve several environmental issues at once, reducing sediment in the reservoir and maintaining the natural ecology of the Colorado River on its path to the sea. It is also the final feature of a reinvented Hoover Dam, which can now be unveiled. The project begins with two massive diversion tunnels, one on each side of the canyon. They will divert the Colorado River around the dam site during construction. The new dam rises 264 meters above the canyon floor. It's 138 meters thick at the base and 20 meters thick at the top. The crest length is 518 meters across the canyon. The new reservoir will contain almost double the amount of water, with a depth of 193 meters at the spillway elevation. Two rectangular-shaped intake towers will stand on each side of the dam. Each tower will be 160 meters tall and draw water from 7 different levels. The water will flow through penstocks in the diversion tunnels to the power plant. The power plant will be equipped with state-of-the-art turbines, capable of generating up to 150 megawatts each. And the 85-kilometer sediment tunnel will help maintain the natural ecology of the river. In the 1930s, the government paid $49 million to build the Hoover Dam, and the project came in under budget and ahead of schedule. In the 1990s, it cost more than $100 million to build the new Hoover Dam Visitor Center. Any reinvention of the Hoover Dam today would cost significantly more. By standard indexing, the cost estimate would exceed $6 billion, and this would exclude the 85-kilometer sediment tunnel. It would also take considerably longer. Just to get started, an environmental impact study would have to be conducted.
An EIS process for building something of the scope and scale of Hoover Dam, 10 years would probably be a minimum. It might even be more like 15, and that's before there would be any litigation. And I would guess that the price would be somewhere between $250 and $350 million to complete that kind of a work.
Then there will be years of research, followed by more years of design, though the actual construction phase might be shorter than the original 5 years. This reinvention team had no more than a few hundred hours to contemplate, calculate, and construct their imaginative design. They point out that a real project of this scope and magnitude would require thousands of hours of work and millions of calculations by hundreds of qualified individuals in a wide array of engineering-related fields. It would be a monumental task, just as it was in the 1930s.
I think it's a monument to possibilities. They could conceive of this dam on paper and draw it out and imagine it in all kinds of ways, but they actually made it happen.
They believed in what they were doing, and they knew they were trying to change the world, and I think that's what gave them a vision towards a goal together. Sometimes I wonder if a group of people today could work together on that level and produce that type of superior product.
What is certain is that the original builders of the Hoover Dam did not see their engineering wonder of the world as a temporary structure.
The future of Hoover Dam is beyond all of us here. Hoover Dam will extend into the ages, will serve this country longer and beyond anything that we can think of.
Just like the Great Pyramids of Egypt, the Hoover Dam may last for thousands of years. Exactly what its builders intended. And if reinvented today, engineers could only hope to create such an enduring monument to human achievement.